Circularly polarized light. A circularly polarized electromagnetic wave propagating in air has an electric field given by E cosine kz minus omega t I hat plus sine kz minus omega t j hat. This wave is incident with an intensity of 150 watts per meter square at the polarizing angle theta p onto a flat interface perpendicular to the xz plane with a material that has index of refraction n is equal to 1.62. Part A, what is the angle of refraction? So, when a light beam is incident at an interface at the polarizing angle, the reflected and the refracted beam make a 90-degree angle. So this is basically the xy plane, and this light beam is incident on the xy plane here, and it's propagating along the z axis. So this angle, the polarizing angle, when it's incident on the polarizing angle, the angle of refraction is called the Brewster's angle. So we can see from Snell's law that N1 for the medium 1, here this is medium 1, and this is medium 2. The index of refraction of medium 1, N1 sine theta polarizing is equal to N2 sine 90 degrees minus theta polarizing. So you can see here 90 plus theta polarizing plus theta b is equal to 180 degrees. So with that, we obtain N1 sine theta polarizing is equal to N2 cosine theta polarizing. Therefore, tangent theta polarizing is equal to N2 over N1, N2 over N1. So we can calculate the polarizing angle theta p to be tangent inverse. So if I check the index of refraction, it's 1.62. So going from air to a material with index of refraction 1.62. So we can see that this theta polarizing is tangent inverse of 1.62, which is 58.3 degrees. So knowing the polarizing angle, we can calculate the angle of refraction, which is 90 degrees minus the polarizing angle. So we can see that the angle of refraction is 90 minus 58.3. So this means the Brewster's angle is 31.7 degrees. So we were asked to find the angle of refraction theta b, that is 31.7 degrees. Let's move on to part B of the problem. Part B, the ratio between the electric field amplitude in the reflected wave and the electric field amplitude of the component of the incident wave polarized parallel to the interface is sine theta p minus theta b divided by sine theta p plus theta b. This result, known as the Fresnel equation, may be derived using deeper analysis. From this relationship, determine the intensity of the reflected wave. In the incident light, note that the EY RMS is EX RMS, which is E over square root 2. While you can see here, the X component is cosine, the Y component is sine, and when I look at the RMS values of these two components, they will be each equal to E over square root 2. That's what is given in the problem statement. Now, Writing the Fresnel equation here, the amplitude of the reflected wave electric field, E reflected divided by the amplitude of the incident wave electric field that is polarized along the interface, parallel to the interface. So that is this is perpendicular. The reflection was from an interface perpendicular to the xz plane. That's xy plane. So polarization in the y direction. So in incident y component. This is equal to sine theta p minus theta b divided by sine theta p plus theta b. So this is the given Fresnel equation. Okay. So this ratio we can calculate. It is sine of polarizing angle 58.3 degrees, Brewster's angle 31.7 degrees, divided by sine of 90 degrees. Their sum is 90 degrees. So this gives us 0.448. Okay, now at the same time, when I look at the average value of Ex squared, the x component of the electric field, that's by definition 1 over 2 pi, integral from 0 to 2 pi, E squared cosine squared theta d theta. So just to remind myself, and that is equal to E squared over 2. So this is a calculation we have done before, and this gives me the Ex RMS value to be E magnitude of the electric field divided by square root 2. So I note that since I have in the incident wave the magnitude of the y component is E, and the magnitude of the x component is also E. This is equal to also E incident divided by square root 2. Why? Because if you look at this electric field, x component squared, E squared cosine squared theta, plus y component squared, E squared sine squared theta is E squared. So Ex squared plus Ey squared is equal to E squared. And they have the same magnitude E here. So their RMS values are equal to the same value, E incident divided by square root 2. So with that, I can write my result from the Fresnel equation tells me the electric field magnitude of the reflected light is equal to 0.448 multiplied by the incident electric field magnitude y component. That is equal to the amplitude E divided by square root 2. So this gives me 0.3168 E incident. Okay, so Ex squared plus Ey squared is equal to the amplitude squared. So that gives me E squared. So Ex incident X component and Y component RMS values are both equal to E over square root 2. So that's basically what I observe here. Alright, so I have determined the reflected electric field to incident electric field ratio from this. Now I can look at the ratio of the intensity of the reflected beam, divided by the intensity of the incident beam. This is equal to the intensity is proportional to the electric field amplitude squared. That's something we know from the Poynting vector magnitude. E reflected square divided by E incident squared. And that ratio we have determined to be 0.3168. So this is 0.3168 squared, which is 0.1004. Okay, therefore, the reflected amplitude, reflected beam intensity is 0.1004 times the incident beam intensity, which is 150 watts per meter square. So we determine the reflected beam intensity to be 15.06 watts per meter squared. So this is our answer to part B, the reflected beam intensity. Okay, so we determined the intensity of the reflected wave. Now part C, determine the intensity I parallel of the component of the refracted wave polarized parallel to the interface. Okay, so we know that the reflected light is 100% polarized. It is 100% polarized parallel to the interface in the y direction, along the y direction, parallel to the interface. That's from the effect of the polarizing angle. Now the incident wave intensity for the x component and the y component are the same, and they are equal to 150 divided by 275 watts. And this is due to the fact that the incident component, y component, and x component amplitudes are the same. So this is due to the fact that E incident x amplitude and E incident y amplitudes are the same. Now for the refracted beam y component, we have the incident beam y component intensity minus the reflected beam y component intensity. This is equal to 75 minus 15.06. So we find the refracted beam y component intensity to be 59.9 watts per meter squared. Here we have the conservation of energy basically. The incident beam Y component intensity is 75 watts. Refracted beam Y component intensity is incident beam Y component intensity minus reflected, because reflected is 100% polarized along the Y axis. Part D, determine the intensity perpendicular component of the refracted wave polarized in the x direction. Now, since there is no x component of the reflected light, doing the same energy conservation argument here, incident beam intensity x component must be equal to the refracted beam intensity x component. So we find that the refracted beam has an x component with intensity 75 watts per meter squared. All right. And part E, the reflected wave is linearly polarized and the refracted wave is elliptically polarized, such that its electric field is characterized as shown in the figure. So this is the elliptically polarized wave. Determine the elliptical eccentricity, which is square root of 1 minus E1 over E2 parentheses squared. So E1 is the component along the x-axis, E2 is component along the y-axis for the elliptically polarized wave. Now, eccentricity is what we are after. That is 1 minus E1 squared over E2 squared square root. That's what is given. So if I look at, I note that 1 is the x-axis, 2 is the y-axis, y component. Now we know that this ratio is also equal to the ratio of the intensities. So this is 1 minus intensity of the refracted wave, x component, divided by intensity of the refracted wave, y component, square root. So let's double check. E1 is the x component and E2 is the y component. So for the now, according to this figure, the one that has the largest number is the x component. The one that has the smallest number is the y component. And therefore, we will find that this is 1 minus. Now we have found the intensity for the x component 75 watts per meter square and y component 59.9 watts per meter square. So if I take 75 over 59.9, this will be greater than 1. So this would be an imaginary number. So it must be that we are referring to I refracted y over I refracted x here to get a real answer. So this means this is going to be 59.9 watts divided by 75 watts in order to get a positive real answer for the eccentricity. So this will give me an eccentricity equal to 0.449. Okay, So here, basically, I have associated 1 with the y component and 2 with the x component of the refracted beam. So that is not consistent with this drawing here. But that's what we need to do in order to have a positive quantity for the eccentricity. So that's what I have figured out. And here I have noted the fact that the intensity is proportional to amplitude of the electric field component squared. So for E1 over E2, E1 squared over E2 squared, I have substituted I refracted Y divided by I refracted X component. So if I do it otherwise, then I would get an imaginary number for eccentricity. So this must be the correct convention to use to find the eccentricity in this case. Okay, so in this problem we talked about a circularly polarized light. First of all, this light is incident on an interface perpendicular to the xz plane, which means it is the xy plane. And it's incident on a material with index of refraction 1.62. We want to know the angle of refraction provided that it is incident at the polarizing angle. Well, I know that the polarizing angle and at the refracted beam will have the 90-degree angle between them. They will be perpendicular to each other. And law of reflection tells me theta polarizing is the same for the reflected beam with respect to the normal. So n1 sine theta p is equal to n2 sine theta b, which is sine theta 90 minus theta b. So this angle here is actually, this angle here is the Brewster's angle, 90 minus theta p. So what I have done here is I have written Snell's law. So sine of 90 minus theta is cosine theta. So tangent theta p is n2 over n1, which means theta p is 58.3 degrees. Brewster's angle is 90 minus 58.3, 31.7 degrees. In part B, we are given that the ratio between the electric field amplitude in the reflected wave and the electric field amplitude of the component of the incident wave polarized parallel to the interface is given by Fresnel equation. From this relationship, we determine the intensity of the reflected wave. So writing Fresnel's equation, we find that the electric field amplitude of the reflected wave is 0.448 times the electric field amplitude of the incident wave y component. And for the incident wave y component, because we have ex squared plus ey squared is equal to e squared, that's what I see from this electric field, and the RMS value of the electric field is E over square root 2. So I can see that these two incident wave and x and y components should be equal to E over square root 2 for the RMS values. So that tells me that the reflected electric field magnitude is E over square root 2 times 0.448, which means it is 0.3168. So if the electric field is written this way, the x component magnitude is E over square root 2, and y component magnitude is E over square root 2. So when I add up E over square root 2 square plus E over square root 2 square, I get E square, which is the amplitude of the overall wave. Okay, so the intensity of the reflected beam to the ratio of the intensity of the incident beam is proportional to the electric field amplitude squared ratio, which gives me 0.1004. Intensity of the reflected beam is 150 watts times the incident beam intensity times this ratio. Now in part C, we determine the intensity of the component of the refracted wave polarized parallel to the interface. That is the y component. The incident beam has intensity x component and y component intensity is the same because they have the same amplitude, which is 75 watts. So refracted beam y component intensity is incident beam y component intensity minus the intensity of the reflected beam. This is conservation of energy in a unit time delta t. So this tells me that the y component should be 59.9. The x component of the refracted beam is equal to the incident x component intensity because the reflected beam doesn't have any x component. So this is 75 watts per meter square. So these two are like energy conservation. The refracted beam is circularly polarized and it has an x component and y component, and the eccentricity of the circle is determined by square root of 1 minus e1 over e2 squared. Actually, it should be, according to this figure, e2 over e1 squared, because if it's e1 over e2 squared, this would be greater than 1, right? So maybe it's better to relabel these as so we can do that here. This is actually E1. This is actually E2. To be consistent. Okay, so with that, we know the intensity ratio, refracted beam y component, refracted beam x component, 59.9 divided by 75. So it's square root of 1 minus 59.9 over 75. Then it's going to give us an eccentricity of 0.449.